Right, so I'll talk about, Anosov representations and proper affine actions. To be honest, I'll start with this part and I'll eventually try to come to the Anosov part. So let's start with something kind of an ancient theorem. It's by Beaver-Bach, and of course I will be sloppy with the years. What did he prove? He proved that if you have gamma sitting inside SO in R, semi-direct Rn, and Rn mod gamma is compact manifold, then gamma is virtually in copies of Z. Essentially, you can tile the plane with the square, that's it. I mean, all other tilings are up to a finite index subgroup, the same thing. After that, Auslander and Marcus found out some examples, and he conjectured, well, he tried to give a proof which turned out to be wrong, and it was named as a conjecture. So you take gamma inside GLNR, semi-direct Rn, such that again the same thing, this is compact manifold. Then this is a conjecture. Then gamma is virtually n copies of, well, not n, like semi-direct product of copies of Z. And such a group is kind of called polycyclic. Of course, virtually means up to a finite index subgroup. Right. No, here it need not. Right. This is a difficult conjecture. It is only known for dimension 3, I think, fully, and till dimension 7, it's a paper on arXiv which was taken once back. It has again been reposted, but by important people. So I think it is correct till dimension 7. The rest is still not known. So yeah, but we will not talk about that. We'll talk about something that starts from this question. So then came into picture Milner, and he asked, well, okay, compact might be a very restrictive condition. Why don't we allow non-compact manifolds also? So what about non-compact gamma mod Rn? Does that, I mean, would that still imply this kind of a polycyclic subgroup? And so Margulis, essentially surprising a lot of people because they didn't expect this to happen, showed that gamma can be a free group, can be a free non-abelian group. And the example that he constructed was inside GL3R, semi-direct R3, such that gamma mod R3, I mean R3 mod gamma, is a non-compact manifold. Of course, a free group is way, way, way far from a polycyclic group. So from these examples, it's kind of one particular project that is still unknown, that in general for Rn, what kind of, if you allow non-compactness, what kind of groups can you put here? Except for free groups. The only other groups that are known are Coxeter groups. That's a work by Danziger, Gerito, Cassel. But yeah, we'll not go there either. So let's see. Yeah. Yeah, that's how he does it. So essentially, so that's the next result, which shows that, so if you have, so if gamma is such an example, gamma is coming from Margulis's example, then the Zariski closure of gamma is a conjugate of SO21 inside GL3R. And that's where you do the Schottky. Right, so that's a result, and we will start essentially from that place. This is kind of a introduction. How much time do we have? Good. Right, so the second step is a spatial case, and we will spend some time on this spatial case, which is the case of SO21. So let's take SL2R and let it act on M2R, the space of 2 by 2 matrices. So this is 2 by 2 matrices in the following way. So how do we act? So let's say G is inside SL2R, G and H inside SL2R, and you have a matrix 2 by 2 matrix A, and you act it this way. You take G, A, H inverse. This is your action. G comma H acting on A is defined to be G, A, H inverse. In this case, we observe that this preserves the following bilinear form. So what is that bilinear form? You take two A and B, and you define it to be minus trace of right A and adjugate of B. I'll define what an adjugate is. It's not an adjoint. It's like if you have a matrix, so adjugate of a matrix A, B, C, D is D, A minus C minus B, I think. Something that you, when you product with the original matrix, it gives you the diagonal determinant matrix. Right, so if you do that, then we also know that the Lie algebra of SL2R, which is denoted by this kind of a math fractional, or no, something, SL2R, which is A such that trace of A is equal to 0. The restriction of this dot product onto SL2R is the Keeling form, which just means it's a natural form on this Lie algebra preserved by the group, and this is also preserved by the group SL2R, and this particular dot product have signature. So this thing have signature 2, 2, and the restriction have signature 2, 1. Signature means it's like if you kind of choose the eigenvectors properly, then you have positive, like this 2 is for the positive space-like things, and this 2 is kind of the time-like directions. Yeah. Yes. So what this gives us is it gives us a map from SL2R cross SL2R onto SO22, the group of transformations that preserve a 2, 2 norm. And essentially this is a it's a two-fold cover. It turns out to be a two-fold cover. And so if we come to the projective objects, PSL2R, cross PSL2R, that means because -1, 0, 0, -1, the minus identity is inside SL2R, that creates some problem with geometry. So we want to remove that. So once you remove that, things become nice. So you get an isomorphism between this and the connected component of SO22 containing identity. You have an isomorphism. And the way SO21 is sitting there, SO21 is sitting there by taking the restriction to SL2R, this copy of. And similarly here you have a copy of PSL2R sitting here, because you can take H and G to be the same thing. And this sits inside here diagonally. And these are isomorphic. So what is that? So that means you take a diagonal PSL2R, means diagonal is a map from PSL2R or any group G to G cross G, which takes G to G comma G. Right. So in this case, we'll try to, we'll try to do a special version of the general theorems. Yeah. Oh, right. This is sitting inside this way, G0, 0, 1. That's how it sits right there. Yeah. So here essentially, there you will have the 1, 1 on the diagonal. That will be the vector which is outside. On the rest of R3 it will act. Okay, right. Another thing, this is a little bit of a general phenomenon, but we will mention it, because if you take G cross G, G is a semi-simple Lie group, but you shouldn't care. You should just think of it as SL2R or PSL2R. The rest does not matter, but this holds more generally. So there is an isomorphism between this G cross G and another product of G cross G. Here you have GH and it goes to G, H, G inverse. Here the product rule is the standard one. G1, H1, G2, H2 is G1, G2, H1, H2. And here the product rule is G1, A1, G2, A2. The product rule is G1, G2, A1, G1, A2, G1 inverse. So if you consider these two groups this way, so let's take this product with a dot. And if you define this map phi, then phi is a homomorphism. Moreover, if you have an element G, GT, where T is kind of a deformation of the element G locally, so you start with G, G and you deform it a little bit, then on this side it becomes G, GT, G inverse, and when you take the derivative, you obtain something G, X, where X is the derivative of GT, G inverse, and that's kind of a co-cycle. And this object lies inside G semi-direct Lie algebra G acting adjoint. Now I will relate this with whatever I've done there, and I'll try to present the theory in its all glory. But if you have any questions here, you can ask, because I went a little bit faster here. So it's a product between two copies of G. It's a group, but that product does not have the standard product formula. This group is with a product let's say I define this product to be like this, and I define this product to be like this, then here cross is sitting and here cross dot is sitting. And homomorphism. Homomorphism. A map taking GH to GHG inverse is a homomorphism from G cross G to G cross G, but two different kind of products. And if you just take, you will need to check that phi is a homomorphism, and phi is. Then once you are here, so if you take an element G and you deform it in the next coordinate, in this group format, you're essentially at an infinitesimal level, you're getting an element inside G adjoint representation on its Lie algebra. But this does not matter too much. We'll relate these two in a few minutes. It's okay? Everybody on board? Kind of? Okay. So, right. So now I'll define. Because point is, I have this adjoint representation of G on semi-direct G, which I'll just see where it comes from. I'll relate it. And I want to relate that with G cross G. And you will see everything coming together in the next section. Right? So the why questions will be, how is a different question. Right? So this section is called Anosov representations. Of course, I will not give a general definition. I'll give a rough definition. But before I give a definition, I'll try to tell you what it's trying to generalize. So you have convex co-compact subgroups of SL2R. Okay, I don't need this. What are they? So you want gamma inside SL2R such that gamma mod H2 is convex co-compact. But what does that mean? Well, I'll not tell you. I'll just draw pictures. When you do quotient, such a thing is allowed. When you do a quotient, such a thing is also allowed. What is not allowed such a thing is not allowed. Something that has a cusp. Both these are convex co-compact. This is co-compact and this is convex co-compact. So we are interested in groups gamma, which when you do the quotient, it looks like this. For those group, we have this really interesting property. And that interesting property is if you take any element, gamma inside such a gamma, gamma is diagonalizable with distinct eigenvalues. All such element. Here it does not happen. When you have a cusp in your group, you will end up having something that looks like 1, 1 and something there. We don't want this kind of elements in our stuff. And in case of convex co-compact, they do not come. Right? And Anosov property or Anosov representation is essentially trying to mimic this behavior. So what is the definition of an Anosov representation? In general, in the literature, you will see Anosov with respect to some parabolic subgroup, they say. It's a fancy way of saying that I'll give you a group, a Lie group, let's say SLNR, and you can write it in terms of matrices. You can, and then you try to diagonalize it. It might not be diagonalizable, But what you can do is you can take a matrix A and consider AA transpose. This is a symmetric matrix and this is diagonalizable. And you check for, so then you write down the eigenvalues of this object. And at the kth level, so between mu k and mu k plus 1, there will be some gap. If there is a distinct, like in this case, you have lambda and lambda inverse, right? So if you take the ratio, it's kind of lambda square. Lambda divided by lambda inverse, it's lambda square. And this, not just with distinct eigenvalues, but these eigenvalues are, they uniformly stay away from 1. Doesn't matter whatever element you take. So of course, if you take products of, if gamma is like this, if you take gamma square, you get lambda square, lambda to the minus 2. So it's increasing, that's fine. What you don't want is that, let's say you take gamma and some eta and you take some kind of a long string of words, you would expect, I mean, the eigenvalues, there is no guarantee that they would also increase with that rate, exponentially. But if that happens also, like if roughly the increase rate is same, then it is called Anosov, which essentially it means that if you have, so Anosov kind of if and only if you have gamma and eta, and then gamma times eta have an eigenvalue gap at level k commensurate to individually gamma and eta. Yeah, so it's kind of trying to mimic the case here, that doesn't matter whatever long element you take, you have such a thing. Then you call this an Anosov representation in SLN R with respect to the kth place. Yeah. Right. I deliberately did not write a proper definition of Anosov representation here. But the only thing that you should keep in mind is that for each element gamma, you have a lambda and lambda inverse. The only thing that we require is kind of this, I should write with a different ink, different color. The only thing that we require is that you take lambda of gamma in that particular case. This lambda of gamma should be bigger or equal, some C strictly bigger than 1 for all gamma, essentially, except the identity, the obvious one. So this kind of uniform gap behavior, so they're separated out at the middle. Okay, now let's go back to our case. If we take two elements of PSL to R diagonalizable, lambda inverse, and you have mu inverse, and they're acting on some 2x2 matrix A, B, C, D. Then you observe that this will be equal to lambda A, I think this will be lambda mu inverse, some object A, I suppose. And this is lambda mu B. This will be lambda inverse, mu inverse of C, I suppose. And this will be lambda inverse mu of D. I think this is what you will get, but I might be wrong. There will be small mistakes. Anyway, sorry. isn't it? Here, I don't think you will get, so you'll have lambda A. Oh, sorry, oh, no, I need to take an inverse here, mu inverse. Yeah. So the two elements that I've taken is G and H, but my action was G, A, H inverse, right? So when I do this, on the diagonal, you have such a thing. So when both G and H are equal, so the eigenvalues are essentially you get lambda square, 1, 1, lambda to the minus 2. So we just take the eigenvalues from here. You have lambda square, 1 here, lambda to the minus 2, when G is equal to H. When G is not equal to H, so now you start with G equal to H and you want to take H to be some deformation of G. Like you perturb it a little bit. Then you don't expect this to be 1, both of them. Sometimes this part might be positive, I mean bigger than 1. Sometimes this part, for some gamma, it might be less than 1. In the sense, if you have, so just take two diagonal such objects. So it's essentially saying that if you have two surfaces, then you might not have that all the lengths of one surface dominates the lengths of the other surface for each element. Yeah, so if you deform, that means that is choose GT close to G, then here you might have, so you will get some lambda T inverse and lambda T, so sorry, you might have lambda T inverse for that element gamma might be bigger than 1, or it might be less than 1. A priori, we do not know what would happen, right? But if it is bigger than 1 uniformly, then it will be Anosov. So if it is bigger than 1 uniformly, if lambda T inverse of gamma bigger than equal to C, bigger than 1 for all gamma inside this guy, then it is Anosov. In SL4R with respect to this middle eigenvalue gap. So now I'll pack up with this, relate Anosov representation with yeah. Right.
Writing down the eigenvalues.
Right.
The resonance at 1 is given.
The resonance at, when you deform, it might still stay 1 fully.
Yeah.
There might be cases where it is strictly bigger than 1 always. There might be cases where somewhere it is bigger than 1, sometimes it less than 1, kind of a, you don't know a priori what happens.
But if it breaks the resonance, then we call it Anosov.
If there is a strict gap uniformly throughout, then that's Anosov. Okay. Inside SL4R with respect to this middle gap. Okay. Right. Now I will relate that with this proper action where we started from. Right. Right. So results. That's our fourth section. How, right, theorem. So, theorem by, I think, Danziger, Gerito, Cassel, and a different proof by me later, using work of, Goldman, Labourie, Margulis, and also me and Nicholas Thribe. Anyway, I should have named a few people here, otherwise I'll get a lot of bad karma. So this laburi should be named Gishard should be named. Apovich Lipporti should be named. Then Bochi Potri Sambarino should be named. And also Castle Purti should be named, right? Or Potri most. Right, I'll not individually say who has done which work, but if I don't mention their name, then the thing just doesn't stand. Right, so what is the theorem? The theorem is that, you remember this rho u, this gx that was constructed here? So now let's say, if you consider rho from gamma inside SO21 sitting inside rho t is a representation of gamma inside SO22 with rho 0 of gamma sitting inside SO21, and we define u of gamma to be rho t gamma rho gamma inverse, then u is a co-cycle, and you have a map, so rho u is a map from gamma to SO21, wait a minute, yeah, SO21 semi-direct, it's Lie algebra. How do I write that? SO21 semi-direct S021. That's the Lie algebra. But this thing is isomorphic to the linear action of SO21 on R3. Precisely the group we kind of started with. So anyway, so rho u is a representation here. Then rho u acts properly, which means rho u gamma mod R3 is a manifold, imply rho comma rho t, not rho comma rho t, just rho t gamma implies rho t is Anosov in SL4R with respect to the middle gap. Just wait a minute. Yeah.
So is it some abstraction like you're taking a kind of a discrete subgroup when this co-cycle is matched with discrete otherwise?
Otherwise, you get a discrete subgroup, but it does not give you a manifold. It has really bad. So to get away from the singular points, you need this. So what I'm essentially saying is that if the action that Margulis, the examples that Margulis came up with, in those examples, so along those co-cycles, if you deform, then the representation that you get is Anosov in in SO22 in SL4R. So it has this middle gap that I was trying to show you. In certain directions, I said in certain directions it might stay 1, 1. In certain direction it might have 1 for some gamma, bigger than 1 for some gamma, lesser than 1 for some other eta. And there were very special directions lambda t, where for all gamma, lambda t inverse was bigger than 1, strictly. So the ones that are bigger than 1, those are the directions of the co-cycle where the proper action happens. Now I'll just state a few generalization, well, not one generalization of this result, two generalizations, one generalizations. So one can consider this SO21 and replace it by SON minus 1n and put it inside SONN and replace this object by SON minus 1n semi-direct R2n minus 1 and ask a similar question. And when you do this, the answer is similar. And that's a result by independently by me and Danziger Zhang. But you can also ask the same question, but seen it as this product, because SO22 could also be seen as product of two PSL2Rs, as we had written, which we just omitted here. So second generalization one could try to do is you take G cross G, and now G is any semi-simple Lie group, and inside you take the diagonal embedding of G, and you can ask similar questions. Like for which direction, like if proper action exists, then how does that relate with Anosov representations? Like the same thing, you just replace this SO21 by any semi-simple Lie group, and this Lie algebra by any semi-simple Lie algebra. And here we had replaced this from, like there's a two version. SO21 is a Lie algebra, which is also the linear action of SO21. So this is the adjoint action, and this is the linear action. The linear action was already generalized. The adjoint action is a generalization in process, kind of. We have a result which is not on archive yet. It's a ongoing, I mean, we are adding some other stuff to it. It's ongoing work. So answered in an ongoing or yet on archive work. By me and Kobayashi, T. Kobayashi. Joint work. Yeah, so I think I'm done.
Any question and comment?
Orbifold is fine. I mean, as long as there are only like finite order bad points, yeah. I think that's what you call an orbifold, right?
Yeah, sure.
I don't want infinite bad points, like.
Right, so just finite.
That's fine.
I mean, I have a vague question.
Yeah, yeah.
You can just stop after.
Yeah, no, please, you can ask.
The
Yeah.
vague question is, why does the breaking the resonance, what's the connection between breaking the resonance and getting into that?
Yeah, so a picture that I wanted to draw, but I did not. I'll draw the picture now. It has something to do with, where do I can draw it here, yeah. So I'll just draw the fundamental domain for, this is a work by Todd Drum. So he gave a explicit construction of a fundamental domain for the examples of Margulis. So what he did is you take R3, you draw the light cone, right? Now something weird is going to happen. So what you do is you just draw a line between, not draw a line, I mean, let me just, And the other one is somewhere here, which should okay. And you have seen from above line like this, right? So you have the light cone. Here there is a hyperboloid sitting, which you look from above, gives you the disk model, the Poincare disk model. A curve in the Poincare disk, geodesic in the Poincare disk model gives you a plane, intersection of a plane passing through the origin in this case. You take that plane, chop it off, only keep the part that is inside the two light cone. And where it meets the boundary, those are two lines. From those two lines, you can draw tangents to this object. Take half of the tangent. And in the same direction, there is one choice to make. You can take the other half, and in this case, the other half. That's fine. Or this one and this half. So we also know that free group has an action on the disk. The Schottky action that you're talking about, you have something like this. So correspondingly, I can draw a horrible picture. Well, pretty nice picture, but if I draw it, it will become horrible. Seen from above, you have these four lines, and from each of them, these tangent planes are kind of coming out. Right. So that will kind of give you almost a nice action. The quotient is almost a manifold. What is the bad point? The bad point is the center. All the elements fix this. So this is a fixed point of the action, and you want to remove this fixed point. And when you remove this fixed point, there the gamma, the eigenvalue gamma t and lambda being strictly different, like lambda t inverse being bigger than 1 means they're strictly different. That being strictly different means here it separates. It doesn't intersect the cocycle level. And to have a proper action, you want to kind of remove this bad point by adding cocycles so that it spreads out. There is no intersection. Whenever a gamma t change happens with 1, here you get an intersection. So that's how these two are essentially related with each other. Yeah. I think it stopped. Oh, you stopped. Oh.
No more question next time.
Oh, sorry. I just forgot to thank the organizers for inviting me to give a talk in the beginning of the lecture. So, yes. And for having this really nice conference. Good.